pleasure and case of being as fortunate for having amidst us Professor Sumit Ganguly from the Department of Computer Science and Engineering, IIT Kanpur, with us today. On a very auspicious day, in fact, today is Buddha Purnima, where Buddha is believed to have been born and also had his enlightenment and also Mahasamadhi. Thrice blessed day. So, on behalf of RKMVERI, I extend a warm welcome to Professor Sumit Ganguly. And he has come all the way from Kanpur exclusively for this seminar, just to help us understanding this Johnson-Lindenstein lemma. As we have already are aware that is the topic that he will be discussing, step-by-step derivation, and also its potential applications, more focused on the dimensional reduction aspect. And just to give you a brief profile about Professor Ganguly, he himself is an alumnus of IIT Kanpur. He was a BTech student there and he completed in 1987 and then did his master's and PhD from University of Texas, Austin. That was in 89 and 92. So, and he has been with Kanpur, IIT Kanpur for the last 27 years or so. And we are extremely fortunate once again to have him here. And without much further ado, I request Professor Ganguly to start his proceedings. But just before that, Saurabh Maharaj is here. As a token of love and appreciation, we have a small gift that we would like to hand over to Professor Ganguly. Maharaj, you can just hand over.
So another one point, probably he has PhD from the
yes.
Silver shirt. So you know that the Galatian book, that's quite interesting. It is already another package.
Packing is. Yeah, I forgot to mention that. That's very important. So it's Abraham Silberschutz. So he's, as you all know, is a very popular computer scientist, has written books in database and operating system. So he was his PhD student. Over to you. Thank you.
Yeah, good morning. So it's a privilege to be here, and I'm not all that distinguished at all. It's really a big privilege to be here. This is a very hallowed place, and I've never been. It's a big privilege to be here. Maharaj is here. He was very famous even in IIT. Yes, he's very famous.
He's more famous now there.
He's very famous everywhere. So today I will let me briefly discuss, state the Johnson-Lindenstein lemma so that you can try to understand why is it so interesting, and then we can, depending on your, where should we start from? Depending on where do you want me to start from, then we can start from there. So this is the Johnson. Okay, so the idea is something like this, that let's say you have a vector x1 through xn, n-dimensional, and n is quite large, okay? N is very large. So think of it as either a video or an image or something which is, so n can be in millions or larger, right? So now if you want to do anything with the geometry of this n-dimensional space, so you're in Rn, right? So we can write, say this is your x, right? And x is in, so I'll use this notation. This means this is Rn, R cross Rn times. So this is part of that Rn. It lives in Rn. And you have a geometry, you have a standard Euclidean geometry. So this is one thing that we'll maintain throughout the discussion, that we will only look at Euclidean geometry. Our geometry is Euclidean. If you want anything beyond Euclidean geometry like L1 norms, LP norms or something, this doesn't work. And a lot of things don't work. Okay, but Euclidean geometry has this beauty and it works very well with linear algebra, as you have seen. It works very well here also, and we'll use a combination of statistics and linear algebra. Both work very nicely. So now if you want to do anything with, say, you are given a set of points and you want to get the nearest neighbor, there are a whole lot of geometric calculations based on distances, pairwise distances. And if you are in high dimensional space and some things get very expensive as a function of n, they're often exponential in n, sometimes if not high polynomial in n, so they are not very easy. So the whole purpose is that let's say that you multiply this by some matrix A, which is say m by n. Okay, so then this becomes Ax, but then this Ax is only m dimensional. So you start with something which is n dimensional. You apply this. This is a random matrix, by the way, because it can't be deterministic. It can't be use linear algebra. Okay, you have, if you have a m by n multiply a by x, you have an n minus m dimensional null space, which means n minus m dimensional vectors will go to 0, which means your distances can never be preserved, right? You have a huge set which cannot be preserved. So this doesn't work. So this is a random matrix. Okay, so this is a random matrix. And now the point is, relax here. We want to, instead of working in n dimensional, we want to work in this m dimensional, which is much lower dimension. And yet distances are approximately preserved. What does that mean? So let us say that there are points. Okay, there are points y1, y2 through yn. This is not powers, these are just points, distinct point. Say call this say y, some yk, and they all are sitting in Rn. So these are k points, and k is large. Okay, so k is also, you know, much larger than 1. N is also much larger than 1. And we would like to preserve the metric space. See, if you just Rn is a metric space, but if you just consider n points, like k points, then you have pairwise k, choose two distances between them, right? Can you preserve all of them? If you can preserve all of them, roughly the geometry is preserved. What we want is something like this. Okay, so this is the wish. The wish is that we want that norm of if I apply Ayj and apply Ayi, and I take the Euclidean norm, L2 norm, right? I'll just define it. This is a notion of a distance. This is in m-dimensional space, and this is within minus or rather divided by norm of yi minus yj. This is in n-dimensional space. This is less than 1 plus epsilon and is greater than 1 minus epsilon. Epsilon is some parameter. Epsilon is some accuracy parameter, right? So epsilon is m will depend on it. M will eventually depend on it, and we'll do the derivations. Point is, this is something what we want is, you cannot preserve distances exactly, no chance, because you will have a huge, so randomized, this is so-called randomized preservation of the metric space. Metric space meaning pairwise distances. So any distance between yi and yj is approximated to within 1 plus minus epsilon factors between, instead of taking yi and yj, apply a to it, and apply a to yi, apply a to yj, now take the distance. This is an m-dimensional space, this is an n-dimensional space. M is much smaller, and yet distances are approximately present. So now if you do whatever calculations you want, geometry-based, nearest neighbor calculations, volume calculations, area calculation, other calculations which are geometry-based, they will all transfer. Because you have this beautiful property, you have this strong property that but you are losing a little epsilon. You are losing a little epsilon and hugely. Instead of something which is in order of n to the some power, now it is m to the power, m is much smaller. And how much smaller, etc. That you will see by the time we finish the derivation, how large is m. But let me just state this. There is, however, one catch here. You can't do this also, even this is not possible. So this, you want this to hold for all 1 less than or equal to ij less than or equal to k. You want over all pairs, right? And this whole thing holds with probability 1 minus delta. There is an error probability. You can't avoid it. So now with high probability, now say take delta to be equal to, for example, 1 minus 1 over n to the 5, right? N is a million to the 5 is very large, so almost with probability 1, but not quite probability 1, there is an error probability. So this whole thing holds with probability 1 minus delta. So there are two parameters. One is the epsilon, one is the delta. Delta is called the confidence, 1 minus delta is the confidence of whatever you are proving, and your epsilon is your accuracy parameter. So typically you can have, say, 99% accuracy, which means all distances are preserved to within 1 plus minus 0.01. So pretty good actually. So, and these are all parameters, right? And what we will show is, this is the Johnson Lindenstrauss. The lemma is that there are distributions of A. So A is a random matrix. That means every entry is chosen at random from some distribution, which we will use it. There are such distributions on A such that for m greater than or equal to some constant by epsilon squared log of k, above property holds. This metric preservation property holds. Okay. The approximate metric preservation property holds. This is the result, and notice a few interesting things. So we'll prove this. The whole point of our discussion is to step by step prove this. This does looks a little odd, but main thing is try to see what it means. All it is saying is epsilon and delta are two parameters. The closer the accuracy, the greater the m, it is 1 over epsilon squared. If you make it smaller and smaller, this becomes larger and larger, n is quadratic essentially. This, however, has surprisingly nothing to do with n. It doesn't matter what the original Rn it was sitting in. No matter how large it is, it doesn't matter. It only matters on the population, k. How many are you preserving approximately? Delta always remains, so delta cannot be ignored. So this is the GL lemma. Okay, and this then approximate metric preservation is this property. So this property holds. C is a constant. C is a constant. C is some constant. As we prove it, we will depend. And this is will depend a lot on exactly what distribution you're using. And there are, by the way, many distributions. And now there are very good exercises that we do one distribution. We'll spend some time slowly building up one distribution, which is the simplest distribution. And then you can think of many other distributions that also satisfy this property. And those distributions are also not all equal. Some are faster than others. That means computing AX will be faster for some, but I will start with the normal distribution, which is not so fast.
So this means that for small dimensions, really we have no method for dimension.
No, these are very high.
Are there any other methods?
No.
Like for 3 dimensions?
No, 3 to 2 doesn't work. But n here is in millions or something much larger. Then it will work. So lots of applications. In machine learning, you are trying to do, say you want to do some.
M will be certain number.
M
It will not be very small.
M cannot be. So now you can plug in let's say epsilon is 0.05, I don't know, and k is say 1,000 points, k is million points, and you just do the arithmetic, it's not so small, it's a few hundred easily.
Because computational geometry generally work with the smaller dimensions. So if the results are helpful there, then probably we can apply.
That won't work. This is not that small. So you start with something huge and then you bring it down to something medium. You can't bring it down to one dimension or two dimension.
I was wondering whether there are other methods. So this method cannot work.
There may be other methods. Sampling is always there, right? Somehow you can sample. All geometry applications. Machine learning, you have an optimization problem. Instead of optimizing in your original n-dimensional space, you translate it to the lower dimension and optimize. After all, it's Euclidean geometry. As long as your distance measures are Euclidean, this will work.
How is it helping machine learning?
Because it reduces the dimension. Usually machine learning works with high dimensional spaces. They are very high dimensional. So in big data, suppose you are doing whatever, TID, a lot of dimensions. So you bring that dimension down to something lower and now do your calculations in the lower dimension. As long as you stay in Euclidean geometry, it will work. If you change geometry, it will not work.
So, what is the mathematical expression for a lower bound domain? So, what is that nothing works?
No. This always works. This is always true, except that.
So, suppose I want to prove it mathematically that it does not work for 30 dimensions.
No, it works for all dimensions because this is a general theorem.
So, for the reverse statement, we don't have any hold on the lower bound that it works for this dimension.
It works for everything, except that it depends.
For an n which is smaller than c by epsilon square log k by, do we have
There are lower bound proofs. That that original Johnson-Lindstrauss is actually at a lower bound. This was proved after a lot of effort sometime around. This is tight. This is tight. So it is surprising that they didn't prove it. It was proved much later after a lot of effort. It was proved that this is tight. And the proofs are not easy also. But yeah, it's tight. So somehow the original proof. Constants are this is leave it as a constant.
And epsilon depends on it.
No.
Epsilon
Epsilon is your parameter. M depends on epsilon and delta and k. It doesn't depend on n. Somehow surprisingly, it doesn't depend on the original dimension. So no matter however large it may have been, it only matters how many there are and epsilon delta.
So it's very useful for the big data analysis, right?
Very useful. It's a base. I mean, how else do you bring down the dimension? It's not easy to bring down dimension. There are other ways, but this is the most standard. As long as you stay within Euclidean geometry. Notice that this is Euclidean geometry, right? Right? What is the norm of x? Norm of x is equal to x1 squared plus x2 squared and so on. Square root. Right? And norm of x minus y is equal to x1 minus y1 squared plus and so on. Xn minus yn squared whole. Right? This is the distance. This is the distance. Euclidean level. This is essential. Otherwise, this fails. No, delta and epsilon and delta are not dependent on distributions. It will eventually, M will depend on them. Distribution doesn't matter. M will depend on it. C depends on the distribution. If you change C, some things work a little better than others. But fundamentally, things are the same. Is the purpose clear? I mean, this is the motivation. This is why this is of interest. Okay. So now let us go step by step and try to prove this. Right. So
are Y1, Y2, Yn are fixed, or are they?
yeah, these are fixed. these are fixed, and somehow surprisingly, the distribution is independent of y1 through y. It works for all k. It doesn't matter what you chose as your y1 through yk. So it matters only on k.
This matrix A, you randomly
Yeah. Yes, yes.
Oh, you are given an input here.
It doesn't matter. Huh.
And you generate
It's
a
oblivious.
matrix A and combine them.
Yes, we are oblivious to the input. We don't care for the input. That's a very nice property. That's what Professor Shirish Maharaj is saying. It doesn't depend on on the points on y1 through yk. A does not depend on it. It's a very fundamentally oblivious to your input. It's the same. You choose at random. Before or after, it doesn't matter.
Can be used for various.
Yes, you can take satellite images or something, apply this and bring it down to a much smaller image, and it will still preserve a lot of things as long as your imagery is what you're doing is Euclidean. It's a very nice and fundamental property. It's a good property.
Especially in the world where we are used to handling such large data, millions to billions of
Yes.
data, some way of
Bringing it down,
using the behavioral geometry that
or roughly, yes, this is very useful. The problem is people may not always use Euclidean geometry. They may use L1 distance, they may use something more complicated, then it will not work.
Probably it will work for FT also.
No, it doesn't work for anything other than p equal to 2. It doesn't work because then it becomes a lot more complicated. And people have worked a lot once on this. So this is actually, those who are interested, it's an entire area on its own. This and the questions that you are raising, these have been raised and addressed, and either their answers are not always easy. So again, there are lower bounds which say that then,
Not even 2 plus epsilon kind of thing.
no, it doesn't work.
It
No.
doesn't depend on the shape of the Euclidean geometry, that is like circle. Exactly p equal to 2, it is a complete.
P equal to 2. Yeah. Open source packages, I'm sure there are these machine learning packages will have a use of this. There are pitfalls, you see. This is pretty much, this is what it says, and as it says, it doesn't assume anything more. If your n is very large and this is how many dimensions you need. So you're bringing a high level, high dimensional, whatever you have, image, video, whatever you have, into a low dimensional, and you're approximately preserving Euclidean distances. That may not be image distance unless, it depends on your application. If Euclideans are used, this is pretty good, and log nearest neighbor calculations, all these are preserved, approximately preserved to within epsilon factors. Very good, actually, they're very good.
Application in graph specification. So that the shortest path.
Yeah, that's the problem. It's just not L2. And there are papers which embed graph into Euclidean spaces, and the embeddings have a lot of errors, and it doesn't work well. There are papers in the 90s which did this and didn't work well because the errors are too much. Graph distances, etc., are not L2 at all.
Maybe with some constraints it might work.
Possibly. So we will start with, let's start with some of the proofs. Can I work with normal distributions? Are you familiar? Okay, good. Okay. So we'll start with Z, and this is a notation for distributed as. To begin with, we'll start with N01. This is our standard normal. Right? Standard normal. And as you are aware, expectation of Z is 0 and variance of Z is 1. Okay, good. And the distribution is 1 over root 2 pi e to the power of minus Z squared by 2. And Z takes the support in full R, minus infinity to infinity. This is a standard definition of a normal distribution. This is familiar, right? Okay. So we will use the MGF function, moment generating function. So moment generating function of Z is expectation of e to the tz, but t is some parameter. And this should exist, first of all. So only those values of t where it exists. So in this case, it happens to exist. And this is equal to e to the power t squared by 2 and happens to exist for all t. So do you want me to prove this? I can prove this. If you want, I can prove this. It'll take a minute. But are you familiar with this? Okay, so you can take it as okay. So we'll work with this. So this is the MGF of Z. So now I'll just give one step. This is a very interesting property of normal distributions. Okay, so let's say that you have x is a random variable and x is equal to a1 z1 plus a2 z2 plus ak zk. Okay, a1 through an are constants, right? So they are all constants from reals, right? And zj's are IID normals. IID is a famous acronym, independent identically distributed, right? So IID. So if you take e to the expectation of e to the power of tx, right? So that by definition is e to the power of a1 z1 plus ak zk, right? The whole thing. And that you can write as e to the expectation. And that is expectation of e to the power of t a1 z1 times e to the power t a2 z2 times and so on times e to the power of t ak zk, right? And this is, and now by independence, since the zi's are independent, ai zi's are also independent, and therefore you can, expectation of the product is the product of the expectation because they are independent. So you can pull them out, right? So this is expectation of e to the power of t a1 z1, expectation of e to the power t a2 z2, so on. Expectation of e to the power t ak and zk. Okay, so now what is this? Well, this, you can treat this as, you know, we had this, right? Instead of tz, you treat this as t. Call this t prime. Call this t prime. If you call this t prime, then according to this, this will be e to the power t prime squared by 2. That t prime is nothing but ta1. So it will be, so this will become equal to e to the power t squared a1 squared by 2. This will be e to the power t squared a2 squared by 2 and so on, e to the power of t squared ak squared by 2.
You are taking the normal distribution. But
I'm considering this linear sum, linear combination. Okay.
The properties of linear combination.
So, and assuming they are IIDs, they are not arbitrary linear, they are independent, Z I Z. And now we consider the moment generating function of this. What is the distribution of this? So this is the so-called two stability. Sum of linear combinations of normal variates are normal. That's a very powerful property that we will use. I just wanted to prove this because it is a very powerful property. So this, you open it up, this becomes this, and by independence this splits. And that, you just apply this formula, t times z is this. So now instead of t, ta1 plays the role of t. So you take, instead of t squared, you get ta1 squared, ta2 squared, and so on. And now if you just simplify this, this is just e to the power of t squared a1 squared plus and so on ak squared by 2, right? And this is e to the power of t squared, and think of it like this, norm by 2. This is called 2 stability, L2 stability. Linear combinations of IID N01s with whatever the constants are. This, okay, by the way, MGF, this is the MGF, right? There is a very famous theorem of when you work with MGFs or Fourier transforms or anything, is that it is invertible. But inverse functions are not easy to compute, very hard to compute. So, but it is invertible, which means that if you can find if you have some random variable whose MGF is of this kind, right? So more generally, if you have n mu sigma, then you can mu sigma squared. That means expectation is mean and variance is sigma squared. And let us say that y is distributed like this, then expectation of e to the power of ty would be equal to e to the power of t mu plus sigma squared t squared by 2. It's just a matter of it's a minute to write it, but you must have seen this. If you have seen so much, then you must have seen this, right? And there is this big theorem from analysis which says that Laplace transforms or MGFs or Fourier transforms, they are all invertible. So which means it's useful in the following way. Inverse functions are not easy to compute. How do you get, so what is the distribution of x? Well, you know that this has the same distribution. It has equivalent means same as any variable y whose distribution is n0 norm a squared. You go backwards, you calculate from first principles, any distribution with this n0 norm a squared as the variance, that will have the same MGF, and hence it is this. You cannot have two distinct functions having the same MGF. Okay, that's the notion of that invertibility. That's a big theorem of real analysis. Same holds for Laplace transform, same holds for Fourier transform, holds for a lot of these famous transforms. So which means that this x, the whole point of all this is that this is distributed as n0 norm of a squared. That is a very powerful theorem. It is called the two stability property of normal distributions. If you have, you must have seen this, but that's why I deliberately did this, because it's a very powerful theorem. Linear combinations of IID normals gives you normal with the constant, I mean the variance being replaced by essentially it's norm squared, Euclidean norm squared. That's a very nice property. We'll use this. Okay. So now we will, so as you can imagine, if you think of this matrix as A, so, and say take your ijth entry. Ijth entries are all distributed as n01. Okay. This is just a normal matrix. A normally distributed matrix, every entry is n01 IID. Right? It's very simple. It's very simple. Now, let us write this as y. Y is equal to ax, right? And let us try to get the distribution of, say, the jth of the ith row, ith coordinate. So let's say that y is equal to ax, right? And aij are all distributed as n01 IID, right? Okay. So now what is the ith coordinate? Ith coordinate of x is equal to axi. And what is this? This is, let us say that this is a prime I, let me use this notation. Prime is the row and otherwise it's a column. So a prime I is the ith row. Ith row. It's a row. Okay, so you're multiplying the ith row with x, so that's what you give the ith coordinate. Okay, and this is equal to ai1 x1 plus ai2 x2 and so on, AIN xn, right? And this we know is distributed as normal 0 norm of x squared. We just proved this, right? We just proved this. So the constants are x1, x2 through xn. We know that aij's are normally distributed. The constants are x1 through xn. So this is norm of 0x norm x squared. Directly, see, this is a very nice property of normal distributions. This kind of makes a lot of things very easy. This property is called two stability. Two stability, two stands for L2 stability. Two stability of normal distributions. It is the only distribution which has this property. No other distributions can have this property.
That is the crucial factor.
Yeah, it's a very crucial factor. We use it. For now, it's a crucial factor. You can change this distribution, and once we finish and we are happy with the proofs, then you can see why other proofs might work and where do they work. But as a proof, this makes it a lot simpler. So you see that yi is this for all I, right? I equal to 1 to m. All the rows. So they are also identically distributed, right? Okay. Okay, now we need to look at by the way, we need to look at norm of ax squared is equal to norm of y squared, which is equal to y1 squared up to yn squared. We need to look at this, right? We need to see how far does it deviate from original norm x squared. We need to understand this. Okay, so just a moment. Without loss of generality, you can assume norm of x is 1, because if not, it's on the unit sphere. If not, it's somewhere out. So it's alpha times its distance is alpha. See, because if norm of x is equal to alpha, then if you apply a to x, this is equal to a times x by norm x times norm x. You just pull it out, it doesn't make much of a difference, right? So this is equal to norm x, a of x by norm x. Pull it out because A is a matrix. So it preserves norms. So A alpha times x, alpha will come out. So it doesn't matter, right? Norm x will come out. So therefore, without loss of generality, it is a scaling matrix. It scales. If you make it double, then the answer is also double. Right. So that's all. So therefore, without loss of generality, just assume that norm of x is 1. Okay. So if you assume this with this, it follows that this is the same as n01. So you started with n01, now the linear sums are n01. Now see the beauty of this. Okay. Now time to look at gamma distributions a little bit. Have you seen gamma distributions? Chi-squared gamma distributions. Okay, let me just I'll just introduce you. Tell me what looks good and what is not so good, and then we can cover some of this.
We could have put in the class book. And then you didn't have to be this so much.
Oh, okay.
It's okay, it's okay.
Achha.
Now we have just what I say AC here.
So let's take a look at a little bit on gamma distribution. Okay. So gamma alpha beta. So there are two parameters. It's a 2-parameter distribution. This is shape and this is scale. Never mind. So the distribution is something like this. If x is distributed as f of x is x to the power alpha minus 1 e to the power of minus x by beta divided by gamma alpha beta to the alpha. And the support is x is greater than or equal greater than 0, equal to 0. It's positive side, positive. Okay, it kind of looks something like this. It depends on alpha, its shape changes. Okay, no negative. Support is only on the positive side. Okay, that's how it looks. Okay, are you familiar with this? Okay, good. Okay. So expectation of the MGF. So e to the power of tx. Okay, any guesses? It's you have to do it. It takes a few minutes to do it. So let me write it, and if you are happy, then I can go on. Otherwise, I'll prove it. It is 1 minus beta t to the alpha, and it is defined only for t less than 1 by beta. On this side, it's minus infinity. T cannot be more than 1 by beta, otherwise this will blow up. Right? Is this? Are you comfortable? We can derive it, or if you want, it's just a matter of integral. It's just you can. Yes, you will find it everywhere. This is very famous. Are you familiar with it? Is it? Okay, fine. Very good. There is a very nice property of gamma which we will use here, which is that let us say that x1, x2 through some xk are IID gamma distribution with parameter alpha j beta, j equal to 1 to k. Okay, which means that x1 is distributed as gamma alpha 1 beta, and so on. K is distributed as gamma alpha k beta. It's a little odd. This is the first time. See, it violates. Normal is very nice. Arbitrary combinations of linear combinations of normals are normals. Okay, this has a nice property. So what is the expectation of e to the power of tx1 plus and so on up to xk? That is equal to expectation. Again, the product will split because they are independent. So e to the power of tx1, expectation of e to the power of tx2, so on, it will split. So on, e to the power of txk, and this is equal to 1 over 1 minus beta t to the power of alpha 1, because this is of this type. And this next one is 1 minus beta t to the alpha 2 multiplied and so on, 1 over 1 minus beta t to the alpha k, right? And this is 1 over 1 minus just, and the nice thing is beta is the same, right? So the alphas add up in the exponent. So you get alpha 1 plus up to alpha k. What does this mean? Again, by going back to that real analysis, that big theorem of MGFs, this means that this has the same distribution as gamma alpha 1 plus up to alpha k and beta. I need this here. I'm coming to this. Right? Arbitrary sums of gamma is not gamma. Sums of linear, only sum of gammas, provided they have all the same betas, then the sum is also gamma. This is a very big restriction. Now come back here. Let's come here. If y is distributed as n01, then y squared is distributed as chi squared 1. It's also written, it is the same as gamma 2 half. Are you familiar with this? I can, if you want, I can prove this. but it's just you have to go back to first principles and show that if this is the distribution, then it's square. Square is always non-negative, right? The square has a gamma distribution of this, and it will come out to be this. It takes a minute or two of work. This is also very standard. You can accept it. It's not a big deal. Chi-squared is the same as gamma 2 half. That is chi-squared 1. And chi-squared m is just a notation for gamma 2m half. It's just a notation. Chi-squared is a special case of gamma because it is the square of normal distribution. Right? Okay, so now come back to this point. Norm of ax squared is equal to y1 squared plus up to yn squared. Now each of them, y1 squared is distributed as chi squared 1, so on, m. Ym squared is distributed as chi squared m. 1. They're all distributed as chi squared ones. They are IIDs, right? Because they start the matrix, the rows, the entire matrix is IID. So every row is IID. So finally, what is norm of ax squared? Norm of ax squared is distributed as chi squared m because it is the sum. Same thing here. Same thing here. Chi squared m is actually the same as gamma 2m half. See, beta is held constant, the m's add up. M's are all 2. Chi squared 1 means alpha is 2, beta is half. Beta is half is fixed. So therefore, when you take the sums, they just add up. So you get 2m, gamma 2m half. Right? Is this
Not so easy, not so easy.
it's a combination of a few properties of normal distribution and gamma distributions that makes this work. So finally, what do you get? Finally, you had y equal to ax. We know that norm of x is 1. What is norm of y squared? Y squared is distributed as gamma 2m half, same as chi squared m, chi squared m. Now we are left on this very small one thing. We have to find the value of m for which this concentrates, right? So, and that's then your fruit. This is a distribution. Finally, now we are kind of almost close to being done. You started with an Rn. You started and you got a vector. You took its norm. Now you know its distribution. Now you have to figure out how close is it. What is this expectation, by the way? What is the expectation of norm y squared? This is alpha beta because it is gamma, which is 2m into half, which is m. Which is good, right? Because the square of every row gave you 1. That was the square. The variance was 1, right? That's the expectation of the square. So you add m of them, you will get m. That's the expectation. Nothing, no surprises here. Right? How far are you from m? So how much can it deviate? That's the only question, right? So I'll use Markov's inequality. So the probability. So we are now in this zone. How large should our m be? How large should it be? So norm of y squared minus m is greater than some t. And I want t to be epsilon m. So we can just write it as some epsilon m. So this is we'll use the exponential moments method, right? So this is equivalent to, this event is the same as lambda norm y squared minus m is greater than lambda epsilon m. And this holds for all lambda greater than 0. Event doesn't change. You're just changing by multiplying by any constant, right? And this also is the same as e to the power lambda of norm of y squared minus m. is greater than e to the power lambda epsilon m. This we will continue. Okay, this. So lambda is greater than 0. Exponentiation is a monotonic function, so it doesn't change the event. Exponentiation. So this, are you familiar with Markov inequality? Okay, so very good. So by Markov, and now we use Markov's inequality. So Markov's inequality, this is less than or equal to the, by the way, this is an exponential random variable, right? This is the random variable, non-y squared. And e to the power of anything is never negative. So Markov inequality holds. It will work because it works for non-negative random variables. That is never a problem. So this is e to the power of expectation of lambda of norm of y squared minus m divided by e to the power of lambda epsilon m. Right? This is direct Markov's inequality. Simplify this a little bit, and then we'll have to calculate this. This is equal to e to the power of minus lambda m, expectation of e to the power of lambda norm of y squared divided by e to the power of lambda epsilon m. By the way, what is this lambda norm of? This is the MGF. This is the moment generating function of non-y squared, which you know is gamma 2m half. So this I can just substitute, right? This is the same as 1 over 1 minus, oh, this is, I think we did the, this is fine, other way, half 2. M by 2. So this will be 1 minus 2 lambda to the power of m by 2. Now our whole business is much simpler. You just have to see how it concentrates. How does it? See, this works for all lambda greater than 0. So therefore, you can choose any value of lambda greater than 0 to minimize this. That's the whole point, right? You want to minimize this and make it as small as possible. And that's the smallest value possible in the feasible range of lambda greater than 0 gives you the minimum, right? And that's the whole point.
Okay, this is basically you are trying to now say what is value of what can be the value of
Lemma. M.
What is the value of m? What should be m? How large should be m? You know that it's pretty good with respect to expectation. Expectation is good. This should be m by 2 into 2. So how large should be m? Clearly, if you use central limit theorem, I never used. Holds for all n. It holds for all n. I never used. A good point. It's a good point. It never used for anything for n. No properties of n are used. So now we just have to get a bound on this. So if you like a bit of some analysis, so we'll do the little analysis and that's it. And otherwise we are very close to being done. So these steps are called the exponential moment method. Sure.
You have to take some question answers.
Okay, we can take questions. No problem, no problem.
So you had this y square expectation of the norm is m.
Right.
And you prove that it is highly concentrated.
No, not yet.
Not will prove.
Yeah.
So my question is simply what insight can we get is suppose I have several vectors, norms are all equal, then can we say they are distributed on a spherical surface of sphere of radius m?
Well, see, it's a gamma distribution. So it goes from 0 to infinity, not on the spherical sphere at all. So you want to show that it kind of concentrates around it, around its expectation. Most of the probability lies within 1 plus minus epsilon of m. And that won't happen unless m is a bit large. In fact, that it does happen is quite surprising, at least to me, it still remains surprising. That it does concentrate. Many things don't concentrate, but this does concentrate. Okay, so all we did was we said that, okay, look, finally we did y equal to ax and its norm squared has this distribution. So as you increase m, this will concentrate around m, around its expectation, which happens to be m, which happens to be as you would.
So that is what I wanted to know. What is the insight, geometric insight, suppose we want to get that all of them have the same distance. The norm is the distance
No.
from the origin.
See, all of these, each coordinate are y1 through ym. The squares are individually quite different. But you add them and they concentrate.
It cannot be done for other districts.
No, no, this is pretty magical.
Only for normal distribution.
No, there are other distributions, but you have to carefully craft it. I'll give you an example.
And will not be as small.
M will be as small. If you take Rademacher, are you familiar with Rademacher? Coin toss, heads is +1, tails is -1. Every entry is +/- random, coin toss. It has the same property. It's a wonderful property. It's even better, a little better. The reason is, see, this goes through a very cleaner proof. Those proofs are not cleaner, but it doesn't have two stability property. It doesn't have all these properties don't hold. It is not gamma. You have to basically do the calculations. Yeah. So this works even better. It's the concept. And it works. It works, and this is if you are interested in this, take it as a homework problem. It'll take a bit of time because two stability doesn't work. But it's a very nice. There are other distributions also. Let me finish, and then I'll give you some examples which you can try out. And with time, we can also sit and try it out. I mean, they're not all that easy. It'll take some steps, but it works. So we are here. So let's finish this. So we are at this point probably. Huh? I'm going to. I just want to finish one part, and then. So we have this probability that norm of y squared minus m is greater than epsilon m is less than or equal to minimum over all lambda greater than 0, and simplify this. E to the power minus lambda m minus epsilon lambda m over 1 minus 2 lambda to the power m by 2, right? Okay. In shortage of any tricks, I'll give you I'll do my bit, and I don't know any easy quick fix of this. This 1 minus the denominator part. If you pull it to the numerator, this is this, which is the exponent of minus m by 2 of the log of 1 minus 2 lambda. By the way, all my logs are natural logs. Okay, so this is what it is, right? Now, if you take log of and we need to remember that lambda is greater than 0. And by the way, here this works only when lambda is less than half. So even though when we say lambda is greater than 0, it can't exceed half. Otherwise, this won't work. Okay, this won't work. So now we simplify this. Okay, so log of 1 minus log or rather log of 1 minus 2 lambda by Taylor series. Expand this by Taylor series around 0. Around 0. So this becomes equal to log 1 plus minus 2 lambda of differential. So what is Taylor series? So f of x around 0 is equal to f of 0 plus x times f prime at 0 plus x squared. I'll do only two terms, a quadratic, x squared by 2 f double prime of some eta where 0 less than eta less than x. Right? This is essentially Taylor series, or if you like, min value theorem. It's just repeated min value theorem. I'll just do this part. So if you do this, then apply this here. Then log of 1 minus 2 is equal to apply to. So x is your lambda. X is actually minus 2 lambda. X is f of x. X is as a function of lambda, and this is so log of 1 plus if you take this, then you get differentiate this as a function of lambda. This is lambda, then differentiate this, you get 1 over 1 minus 2 lambda times minus 2, and this part is set to lambda equal to, evaluated this. And then lambda squared by 2, second differential of this would be minus 2, 1 minus 2 lambda squared times minus 1 times minus 2. And now this will be evaluated at some eta, and we know that 0 less than eta less than lambda. Okay. Simplify. So this part goes to 0. This part becomes minus 2 lambda by 1 minus, sorry. Yeah. This is lambda equal to 0, so this becomes 1 basically. So this is equal to minus 2 lambda. First term is as expected. This term becomes a minus 2 to 4 to 2 lambda squared by 1 minus 2 eta squared. Right? And what is problem with Taylor series is this is about it. We don't know how close lambda eta is to 0 or to lambda, and we don't know. So lambda, we know that 0 less than eta less than lambda less than half, right? So eta is some value between 0 and half. Now we want this to be greater than or equal to. See, finally we want to multiply this by minus m by 2, right? So if you multiply by minus m by 2, log of 1 minus 2 lambda, this is equal to m lambda, and then this becomes equal to plus m lambda squared by 1 minus 2 eta squared, but we don't know what eta is. So we want to make this as get an upper bound. See, if eta becomes larger and larger, then it becomes, eta becomes closer to half. If you make it half, this becomes infinity. So we can't do this, right? So we set our lambda to be less than 1 by 4, and set 0 less than eta less than 1 by 4, and set eta equal to 1 by 4. And this is therefore less than m by lambda plus m lambda squared by 1 minus 2 by 4 whole squared, with the understanding that 0 is less than lambda less than 1 by 4. We brought it down from half to 1/4. You can go it above also, go to 1 by 3, but you will basically struggle with some bounds. Okay, the bounds will change a little bit, and this becomes equal to m lambda plus half 4 m lambda squared. What is the interesting thing? See, this may seem a little odd, right? But notice that this m lambda disappears. This is so important. The expectation goes. The contribution of expectation goes. So if you now go back here, you get probability of the norm of y squared minus m greater than epsilon m is less than or equal to the minimum of e to the power of minus lambda m minus epsilon lambda m plus 4m lambda squared plus m lambda. You see, this goes. And you are left with essentially a quadratic. Minimum over lambda less than 1 by 4. And this is minimum of exponent of 4m lambda squared minus epsilon lambda m. How do you minimize this? Well, differentiate set to 0, equate, and you get the answer, right? See, this is your function. Call this function some phi of lambda. So phi of lambda is equal to 4m lambda squared minus epsilon lambda m. Right? Differentiate. If you differentiate with respect to lambda, and this is equal to 4m or 8m lambda minus epsilon m. First of all, if you differentiate twice, it will remain positive. So it's a convex function, and therefore it's a local minimum is a global minimum. Right? If you differentiate twice, you get 8m. This part goes away. Linear term goes away. Any quadratic function is therefore, whether it is convex or concave, is completely determined by the coefficient of the square term. This is, if you differentiate twice, you get just 8m. 8m is always positive, so it's a convex function. Convex function means that you equate to 0, the local minimum is the global minimum, right? So if you equate to 0, right, so you get lambda, and let's call this the minimum lambda. This is equal to epsilon by 8. And now we are not so worried. It remains within 0 to 1 by 4 because our epsilons are typically small. They're like 0.1 or something. So this is always between 0 and 1 by 4. Substitute this. So phi of lambda m is equal to 4m into epsilon by 8 squared minus epsilon into epsilon by 8 into m. Simplify. And so what do you get? You get epsilon squared m. Here you get 16, okay, by 16. You should verify the calculations. They somehow all end up being pretty nice, actually. This is always double of this at the time of optimization. Finally, the whole result of this is this very simple property, that what we get is this becomes equal to exponent of minus epsilon squared m by 16. Just one small step remaining. Now I have to show that this is less than, when is it less than delta? When this becomes epsilon squared m by 16 is greater than log 1 by delta. And so that is equivalent to, which is implied by m is greater than or equal to 16 by epsilon squared log of 1 by delta. This is the desired one. You see what we got in what we were discussing in the beginning. This is the final step. If this holds, then this holds. What was missing? There is a small step missing, which is that I did the right tail bound. I did the tail bound on the right. You have a similar tail bound on the left, which is almost identical. It's a little better. If you take epsilon squared less than m minus epsilon m, this will also end up being a little bit better. This will also end up being less than e to the power of minus epsilon squared m by 6, 8 or so. It will become better. If you want, I can do the left bound also, but they are very, very similar. It's a bit easier. Yeah, this is a lot of, it looks like a lot of calculations.
Yeah, linear algebra always looks very easy. But the basic thing
Is very simple. It's very, point is these calculations that they work is not always, they don't always work. You know, it because of, we started with normal, we squared it, we went to gamma, and then we added and we got the additive property, and it concentrates, and now you get, this is Johnson-Lindström's law.
So let us go for question.
This is a good time, to ask questions and just look at it and see if you agree with it. And where, if any, you are finding any issues or.
Great question. Very good.
Yeah. Correct. Oh, see, I differentiated it, set it to 0, it comes out to epsilon by 8. So that is your local minima, and because it is convex, that's also the global minima. The constraint is 0 to 1 by 4. Epsilon is pretty small. So it will always between 0 and 1 by 4. So it works, right? Actually, everything here works. This is a somewhat surprising thing.
I'm not even now I'm not convinced if it should not work for P. For why I am asking is because the distances of P, if it is near to 2, the distances will be somewhat safe. And because the distances will be somewhat safe, the confidence may be low.
And those properties will, if you are very close to 2, then L2 and L2 plus P are close. Hence, inferences on L2 can extend to L2 plus P with a little distortion. That will work. That will work. Your point is right. But here it works. Here it works because the minimum comes out to epsilon by 8, which is within your boundary, which is therefore fine. See, that's what the KKT is simply this. It's a convex function, right? Because you differentiate twice. Then it's a convex. So it's globally convex. So local minimum is the global minimum. And all you need is a minimum. So KKT will work because it's a quadratic. I mean, you don't need much of KKT. It's a quadratic, right? Any quadratic is dominated by the coefficient of the square term.
This is a lemma which is used
Routinely. We use it routinely. Now, you can replace this matrix by plus minus 1 matrix, random toss plus minus 1. And that still works. It works a little bit better also. Constants are better, but it takes more work to prove it because you don't have additive properties and all.
Is there any common family of random variable for which it works?
Like normal is the best, right?
No, not also. I am saying that something superset of normal.
Normal, nothing else will work. Because of 2 stability. Because of 2 stability, nothing else will work.
This work for many distributions. So is there any family of the distributions?
They're all different. So one is this random coin toss. This works.
Is that popularity?
So they are called sub-Gaussian distributions because if you take a Rademacher random coin toss, then its exponential moment is less than or equal to e to the power t squared by 2. It is not equal, but it is actually substantially less. So you can take almost a lot of these analysis you did on MGFs of normal. It will borrow the same things.
So the bound is that. So if it is less than that, then
The bounds will follow, but you have to be careful because you square it and this doesn't work. So squaring of the Rademacher will require further analysis.
Actually, say something more on the application side.
I have a question. Norm of y square is expectation of the norm is 10.
Right,
Then you prove its concentration.
correct.
So here is my question. So if I draw the y vectors on the plane, so it is like from origin I am getting almost all the vectors around the surface of a sphere of radius n. Now if I prove
Radius 1,
n, the nodes say
sum. So each of them is about 1. Each of them is gamma squared, chi-squared 1. So each of them is, but it is.
Actually, I am missing something. Actually, I am not familiar with these things, but what I am this definition p of y square. P of y square, that norm, y, the norm of y. The norm of y which Ax, that is the distance of the vector y from the original.
Correct.
This is I am correct.
Correct.
Now, if I take this, all these x
Coordinates,
vectors,
coordinates.
x vector, I'm not talking about coordinates.
Oh, you take
What
x
I'm
vector.
asking is, you have this x vector total, x. So, and you are getting something. So, x1 you are getting a big y. X2 you are getting.
No.
No, sir. Let me, maybe I'm not the same point. So, I'm talking, so x1, x2, xn are the coordinates of the vector x.
X,
So now when you multiply it by a, the random vectors, you get a vector y.
Correct.
Right? Y has several coordinates, y1,
Correct.
y2, y3.
Right.
But when I'm talking of the norm of the vector y, it means the point, the n-dimensional point, the distance from 0 to that point. That is the f.
Correct.
So now what you end up putting is that is constant.
Right.
Right? So what I am asking you is this. So for most of the vectors, when you multiply by a, the random vectors, most of them are having the distance nearly m.
Correct.
So isn't it same as saying that most of the vectors will lie on a sphere of radius m when you project it?
I am sorry to interrupt. You discussed this thing in my office with me.
No, you're right, but you're right. Yeah,
So
it is within m plus minus.
So there is a well-known result, and there is what you are talking about. There is an insight to it. And then after.
Now, but then we can prove this in a different way, is what I am trying to say. So if we have that node,
So basically, that transformation, it is you take generally m different directions and project all the points on those directions. So it's
exactly.
that is what we are doing.
Yeah, so that is what I was trying to say. So if we have on the sphere M, we again end up putting that these points are almost all the points are on the surface of the sphere M.
But the numbers will be somewhat similar.
Ultimately,
What will be able to
so it will
work
be a
out.
different proof.
So inside, no, probably not. That is what I am saying. Inside might be different, but will be somewhat similar.
But here if we calculate the distribution of the angles between two vectors and prove that it is almost similar,
Possible. I don't know. It's possible. It looks fine.
The students can ask non-technical, non-academic questions also. Will it be okay?
Yeah.
Few questions.
Yeah. Okay.
The tea will come in another 15 minutes, 10 minutes. Also.
Yeah.
So you have to ask questions.
We are a
So you have to ask.
If you want to ask any questions?
Yeah. As the value of see, if you increase m, this exponentiation minus epsilon, hold epsilon constant, let's say. If you increase m minus epsilon squared m by 8, whatever, it will keep increasing, right? Which means that delta will reduce. E to the power, that's your error. E to the power, this right hand side is the error. Probability that this is greater than this, that it exceeds epsilon boundary, is less than this, and this reduces, which means your delta will reduce, which means the error will reduce. The larger the m, the stronger the concentration, the closer it will get. The surprising thing is, this matrix has nothing to do with your inputs.
Yeah, that's hey, but machine learning people I'm sure don't understand.
No, they use it. They do use it, but many of them don't understand.
In the form of a package, not in the form of an algebra. I think the question of participation they means why they need so much of
Because maybe they are not using L2 all the time. They use the regularizers and L1s and all that, so then it doesn't work.
what happened to your all this randomized sampling for like when you were climate tracking the climate, you are
But there is not L2. It's not L2. Not at all.
All these big elephant, small elephant, all go.
Yeah. You need something else there.
Oh, this thing don't work.
This will not work directly. Yeah.
I think L2 works
Ah,
independence of the time.
yes.
Now I understand, because if you what you are doing is you are taking the n direction,
Ah.
then you are projecting. So
Ah,
the distances should be.
they still remain preserved. They are preserved.
But whereas P does not work, P is very larger than 2, for example.
Then it won't work.
Then different
Directions are different.
you have got,
Huh.
distances are.
Even L1 doesn't work.
Students ask,
It's a very powerful technique, and yet it seems outwardly very simple. Yeah. Yeah, you're right. So I didn't go for higher k. I took one point and showed that its distance is preserved. Now say there are k points and there are k choose 2 distances pairwise. So all those k choose 2 distances can be preserved, provided your right hand side instead of being delta is delta by k squared by 2. Now the whole thing is preserved. That's how you get k. That's how you will get that. I wrote log of delta by k. That's the log of k delta by k choose 2. Okay. Because you're preserving that many distances. Yeah. Sorry. But you only want to decrease, right? You want lesser dimension. This is a reduction method. If you do the other way around, you can always put Rn into Rn plus 1. There is no problem. Geometry is preserved. Problem is you can't bring Rn to even Rn minus 1. The whole geometry goes. And yet, you see, you can go from a high to a low and approximately preserve with some loss of confidence. Instead of, you cannot have deterministic. You can think about it. There is no deterministic map even from Rn to Rn minus 1. It's not possible. Just exponent, just too big, infinitely big. So, but yet you have nearly, you're preserving distances. No, I need to optimize this. This is এটাকে, if you want to optimize this, now আমি মুছে দিয়েছি কয়েকটা স্টেপ, কিন্তু এটাকে ডাইরেক্ট অপটিমাইজ করা হচ্ছে, write it in exponential form, then it is m by 2 log of 1 minus 2 delta, and log of 1 minus 2 delta is complicated. এটা হ্যাঁ, direct optimization of log of 1 minus 2 delta you can do, you can try. I never tried. You can try. Is it a convex function? Is it a? It's not an easy function. You want to? So let me understand what you are saying. What you are saying is you optimize this directly. Possible. You try this. Maybe it gives you slightly better bounds. I use Taylor series to make it a quadratic. Possible. Yeah. Differentiate once and set to 0. Is it convex?
Distribution which follows that but not actual follows that. Then there is some error. If the error has been created from the output, then
You are saying that AIJs are not N01.
they are not coming from that exact distribution which follows that
Then you will have errors, and then what is the you have to do the analysis to bound the magnitude of the error. It will lead to errors, and then to bound that is not easy, but you have to do a separate analysis.
One trick is that you have to restrict this to only to this distribution, and then only you get so restrictive. Software implementation হচ্ছে
প্রচুর। But it is already n dimension, right? N equal to 3. It doesn't work. No distribution seems to work. For L1 Cauchy distribution, you can try, but it doesn't have additive property. It has only additive property. It doesn't have. You can't take averages and so on. Those don't work. Cauchy L1 may work a little, but not so easy again. Cauchy is good, but up to a point. Cauchy has infinite variance and normal concentrates. So Cauchy doesn't concentrate. Okay. Okay.
What is series of lecture is something for the student next semester, which will be directly useful in the PhD program and take something.
I can send some problems. You can try out extending this or variations of this, and they are quite rich actually. Since now you understand this is a good starting point.
No, I'm saying next semester if you can come for a longer period. Can you think about any topic which they can be helpful to them?
Compressed sensing, there are these kinds of topics, or there are randomized outcomes.
Less area. This area is too much.
No, but they're good with it. They're you're good. You're very good. Maharaj is also everybody's good.
Something for a week, some 4 or 5 lectures or something. Something about implementation thing. Last time you talked about a lot of implementation of software and that thing. You are good at that also.
We'll see. We'll discuss.
No,
they got it. They got it. The questions are good. They're getting it.
No, something for the student which will be useful. Because last time you talked about a lot of implementation.
That also.
Software implementation.
Okay, please have a
we'll work out later. Sometime for 1 week complete. So listen.
student routine.
তো ভালোই হলো তো বড় বুঝলো তো হ্যাঁ এটা একটু
সিম্পলিফাই করে দিয়েছো
হ্যাঁ
সেটা বলেছো তো, সেই জন্য কাজটা
এটা খুব সুন্দর জিনিস, বেসিক অথচ খুব খুব পাওয়ারফুল, অথচ মানে দুটোই, মানে কঠিনও এবং সহজও দুটোই। আর এটা 1 মিনিট, এটা মহারাজ